Hello everyone, welcome back to SmartBot Sphere. In today's video, we're going to build a bike engine animation using Python. This project is a fantastic way to learn Python graphics, animation concepts, and basic mechanical engineering all at the same time. As I scroll through the code, I'll explain both the engine concepts and exactly what each section of the Python code is doing. Let's begin. Before we jump into the Python code, let's first understand the main parts of a bike engine. This image shows the core components that make the engine work. At the very top, we have the spark plug. The spark plug is responsible for igniting the compressed air-fuel mixture inside the cylinder. When the spark plug generates a spark, combustion occurs and power is produced. Next, we have the cylinder. Think of the cylinder as the chamber where all the action takes place. The piston moves up and down inside the cylinder. The piston is the moving component that receives force from combustion. When fuel burns inside the cylinder, the piston is pushed downward. As the piston moves, it transfers that motion to the connecting rod. The connecting rod acts as a bridge between the piston and the crankshaft. One end is connected to the piston and the other end is connected to the crankshaft. Finally, we have the crankshaft. The crankshaft converts the piston's up and down movement into rotational movement. This rotational movement is ultimately transferred to the motorcycle wheel. Now that we understand the components, let's see how these parts work together during the engine cycle. This diagram shows the four-stroke cycle used in most motorcycle engines. Every engine cycle consists of 4 stages. Let's look at them one by one. The first stage is intake. During the intake stroke, the piston moves downward. As the piston moves down, fresh air and fuel enter the cylinder. You can think of this as the engine taking a deep breath. Next comes compression. During compression, the piston moves upward. This compresses the air-fuel mixture into a smaller space. Compression increases pressure and prepares the mixture for ignition. The third stage is the power stroke. This is the most important stage because it produces useful energy. At the top of the cylinder, the spark plug ignites the compressed mixture. The combustion creates a controlled explosion. This explosion pushes the piston downward with force. That downward movement generates power and rotates the crankshaft. Finally, we have the exhaust stroke. The piston moves upward again. This pushes the burnt gases out of the cylinder. The engine is now ready to start the next cycle. These 4 stages repeat thousands of times every minute while the motorcycle is running. Now let's see how our Python animation simulates this entire process using simple mathematical calculations. Now let's connect the real engine with our Python code. Our animation focuses on the mechanical movement that happens inside the engine. The first step is crankshaft rotation. In the real engine, the crankshaft continuously rotates. In our Python code, we simulate this by increasing an angle value. Using mathematical functions like sine and cosine, we calculate the rotating position of the crankshaft. The second step is the connecting rod movement. As the crankshaft rotates, the connecting rod changes its angle. In the animation, we draw a line between the crankshaft and piston. This line continuously changes position, creating the connecting rod effect. The third step is piston movement. The rotating crankshaft causes the piston to move up and down. In our code, the piston's vertical position is calculated using mathematical formulas based on the crankshaft angle. As a result, the piston moves smoothly inside the cylinder. The final step is the combustion effect. When the piston reaches the top position, we display a combustion animation. This represents the spark plug igniting the compressed fuel mixture. Although simplified, this effect helps visualize the power stroke of the engine. So the entire animation follows a simple sequence. The crankshaft rotates. The connecting rod transfers motion. The piston moves up and down. Combustion occurs. And the cycle repeats continuously. This is exactly the same principle used in a real motorcycle engine, except our version is simulated using Python code and mathematical calculations. Now that we understand both the engine concept and the animation logic, let's move into the Python code and see how each part is implemented step by step. Now that we understand how the engine works mechanically, let's see how the Python code creates this animation. At the top of the file, we import two libraries. The first library is Tkinter. Tkinter is Python's built-in GUI library that allows us to create windows, buttons, canvases, and graphical applications. The second library is the Math module. We'll use mathematical functions such as sine and cosine to create realistic rotational movement. Next, we define the width and height of our application window. These values determine the size of the area where the animation will be displayed. After defining the dimensions, we create the main Tkinter window. The root variable represents the application itself. We then assign a title called Bike Engine Working Animation. Next, we create a canvas. Think of the canvas as a digital whiteboard. Everything we see in the animation, including the piston, crankshaft, connecting rod, and combustion effect, will be drawn on this canvas. The canvas is then packed into the window so it becomes visible. Now let's move to the engine parameters. The variables cx and psi represent the center point of the crankshaft. Every rotation will occur around this position. Next, we define crank_radius. This value determines how far the crank pin moves away from the center during rotation. In simple terms, this controls the size of the circular motion. The rod_length variable represents the connecting rod length. Although our simulation is simplified, having this variable makes the code easier to understand and extend later. Finally, we initialize the angle variable. This variable controls the current rotational position of the crankshaft. As the animation runs, this angle continuously increases, creating rotation. Now we arrive at the draw_engine function. This is the most important function in the entire program. Its responsibility is to draw every component of the engine for each frame of animation. The first statement inside this function clears the canvas. This removes everything drawn in the previous frame. Without this step, the screen would quickly fill with thousands of overlapping drawings. After clearing the canvas, we start drawing the engine body. The first rectangle represents the outer engine casing. Then another rectangle is drawn inside it to represent the cylinder. These components remain stationary throughout the animation. Next, the code draws the crankshaft. First, a circular shape is created to represent the crankshaft wheel. Then we calculate the rotating crank pin position. This is where trigonometry comes into play. The horizontal position is calculated using cosine. The vertical position is calculated using sine. As the angle changes, these coordinates move around a circular path. This creates realistic crankshaft rotation. Once the coordinates are calculated, a line is drawn from the center of the crankshaft to the rotating crank pin. This line represents the crank arm. A small circle is also drawn at the crank pin location. Together, these elements create the rotating crankshaft assembly. Next, we calculate the piston position. Unlike the crankshaft, the piston does not rotate. It only moves vertically. The code uses the current crankshaft angle to determine how high or low the piston should be. This calculation creates smooth upward and downward movement. After calculating the position, a rectangle is drawn to represent the piston. When the animation runs, this rectangle continuously moves inside the cylinder. Now let's look at the connecting rod. The connecting rod is drawn as a line connecting the crank pin to the piston. One end follows the circular movement of the crankshaft. The other end follows the vertical movement of the piston. Because both ends move differently, the connecting rod continuously changes its angle. This creates a realistic simulation of an actual engine mechanism. Next, we draw the spark plug. A small rectangle is positioned at the top of the cylinder. This represents the spark plug used in real engines. The most interesting part comes next. The code checks whether the crankshaft has reached a specific position. When that condition becomes true, the program displays a combustion effect. A glowing shape appears above the piston. The text combustion is also displayed. This simulates the ignition of the compressed air-fuel mixture. Although simplified, it helps visualize the power stroke of the engine. Now let's move to the animate function. This function controls the entire animation. First, it calls the draw_engine function. This draws the engine using the current crankshaft angle. Next, the angle value is increased slightly. This small increase represents crankshaft rotation. Because the angle changes every frame, the engine components continuously move. After updating the angle, the code uses the root.after method. This tells Tkinter to call the animate function again after 30 milliseconds. This creates a repeating loop. The process repeats over and over again. Draw the engine. Update the angle. Wait 30 milliseconds. Draw again. Because this happens many times every second, our eyes perceive smooth motion. Finally, the animate function is called for the first time. This starts the animation loop. The last line, root.mainLoop, starts the Tkinter event system. Without this line, the application window would immediately close. The main loop keeps the program running and continuously responds to animation updates. So to summarize, the entire animation works using 4 major steps. First, calculate crankshaft rotation using sine and cosine. Second, calculate piston movement based on the crankshaft angle. Third, connect both components using a connecting rod. Fourth, continuously redraw everything using an animation loop. These simple concepts allow us to simulate a real mechanical system using only Python, mathematics, and graphics. And that's how our bike engine animation works from both a programming and engineering perspective. Now let's run the code. We use Python space file name.py command. Great! Our code shows the concept we learned how a bike engine works in an animation. This project demonstrates how software can be used to simulate real-world engineering systems. The same techniques can be used to create robot simulations, conveyor systems, machine animations, factory visualizations, and many other engineering applications. If you found this tutorial useful, don't forget to like the video and subscribe to SmartBot Sphere. Thank you for watching, and I'll see you in the next video.